Number 2 on the test review talks about, still talking about correlation. So it says, does a student with a higher GPA, have a better chance of getting a high ACT score? So a scatter plot of GPA and ACT scores is shown below for a sample of 20 students from 2013. So we want to know what's the explanatory and the response. So the explanatory is what's causing the change. So we think people with a higher GPA have a better chance of getting a higher ACT score. So that means GPA is our explanatory, and the explanatory variable goes along the x-axis. ACT is our response. So ACT goes along the y-axis. The direction of this, so it's either going to be positive or negative. So in our case, it's going to be positive. The form is going to be either linear or nonlinear. So it's positive because as we read it from left to right, the data values are going up. They're all kind of closely around that straight line, so that means it's linear. The strength, we want to know if it's weak, moderate, or strong. I would take either moderate or strong here. And now for part G, we want to give an example of a lurking variable that may be influencing the response. So think of things, I'm going to write this up here, things that could be affecting ACT score instead of GPA. Could be things like motivation. Typically students with maybe more motivation in school would probably get higher GPA, and then would study for the test to get higher ACT scores. We also might see test anxiety. That might be a thing in there. It could be, whether or not a person got enough sleep the night before. So there's tons of factors that could be considered lurking variables that would have an influence on GPA, or on ACT scores, sorry, but they're not GPA. All right, for number 3, we've got a scatter plot, and we're going to use this for the next couple of problems. So we have a scatter plot that shows the relationship for accuracy of target shooting based on the distance from the target. So our response variable is the accuracy, and our explanatory is the distance. So think of it as you see, as we're further away, this is a negative scatter plot. As we go from left to right, it's negative. So we see if we're further away, like this value over here, we're further away from our data, our accuracy is lower, right? We're not hitting the target. But if we're super close to it, like up here, we're like right on top of the target, our accuracy is higher. So we want to know which of the following correlations would be reasonable for this data set. Missing something, there we go. So here's the values. Now, since it's negative, that means we're automatically canceling out the positive ones. Now, these are kind of close. You could say kind of B because it kind of does look moderate because we've got some outliers there. So I'd accept B as well. We're going to go with A for this one. It was pretty strong, right? They're very close to our line there. Now for part B, we're going to use the correlation value that we chose in question 2. So we chose that R is negative 0.9. We're going to find what is the proportion of the variation in accuracy that can be attributed to the distance from the target. So proportion of variation is R squared. So it's just going to be negative 0.9 squared, which is going to give you positive 0.81. Now for letter C, we're looking at the following equations to see which one will be the better possible least squares regression line. Now, we know our equation is ax plus b, where a equals the slope, b is the y-intercept. Now, our equation was going down. That means a and b we can cancel out because they have positive slopes. Now we just have c and d. This is where I would look at the x or the y-intercept there. So our graph kind of looked like this. So it started way up here. So it definitely didn't start at 3. That means the only one that's reasonable is part D. So the R is not going to be the slope. So we notice for part C, 0.9, negative 0.9, that was our correlation, our R. That's not the slope. So the slope actually in this case is 3. Now for part D, we're going to use that equation that we just picked to predict the accuracy of a shooter who is 15 meters from the target. So we're going to let x equal 15. So when we plug this in, and we just, evaluate this with our calculators, negative 3 times 15 plus 130, it gives us 85. So is this an accurate prediction? Yes, or it's valid, because 15 is in our range of data values. For letter E, we're going to use that same equation, which was negative 3x plus 130, to predict the accuracy of a shooter who is 30 meters away from the target. So we're going to do it just like we just did, negative 3 times 30 plus 130, which gives us 40. Now, is it appropriate to make the prediction here? In this case, this is not valid due to extrapolation. That means, 30 is out of our range of values. All right, for these next ones, let's see, this is 4 and this is 5. So we're talking about definition of correlation for number 4. So correlation, it describes the direction and strength of straight line relationships. So it's only linear relationships, only the straight lines, and it describes direction, so positive or negative, and strength is whether it's weak, moderate, or strong. Now, confounding, that is when we cannot tell if the explanatory variable causes the response or if a lurking variable does. So confounding, we can't tell whether it's the explanatory variable or a different lurking variable that's causing the change in the response. Right, 6 and 7 are again just kind of more focused on correlation. So number 6 says if correlation between weight in pounds and feet, or height in feet for a human is calculated to be R equals 0.76, what will happen to R if we convert the participant's height to meters? R will stay the same. Correlation does not have units. And then for 7, if the correlation between the weight in pounds and the height in feet for a human is calculated to be, again, R equals 0.76, when we consider the weight to be the explanatory and the height to be the response. So we're starting out, we're saying, all right, weight is the explanatory, height is a response. What would happen if we switch those? If we switch the explanatory and the response variable? So the explanatory is now the height and the response is the weight. Again, it stays the same because correlation does not know the difference between explanatory versus response. You know, the correlation R, it's just telling you like basically how two sets of data are connected. It doesn't know which data set is the explanatory or the response. So if you flip them, your equation will be different. Your y equals ax plus b will be different, but your R would stay the same. All right, so a little bit more about correlation. There we go. If relationship between inches of rainfall in a year and perennial flower height, so in inches, that year has a correlation of R equals 0.69. What does this tell us? So in this case, your correlation is positive. That means as the explanatory increases, the response is increasing. So in this case, as the rain increases, the height of the flower increases. If it was negative, it would be letter B. It would be as the rain increases, the flower height would decrease. But we know that. That's weird. That's not right. For number 9, correlation is always a number between -1 and 1. It can be 0, it can be anything up to 1, and it can be anything down to -1. For 10, correlation is significantly affected by outliers. Remember, outliers are numbers that are really big or really small compared to the rest of the numbers. 11, true or false, correlation can be measured for linear and nonlinear. It's false. It is linear only, which in this class we're only talking about linear. And then number 12, true or false, the correlation coefficient R takes on the same unit from the explanatory variable. That is false again. Correlation has no unit. All right, and the last little bit for this video. So number 13, we have a recent study found that how much money spent on a wedding directly correlated to how long the marriage will last. Specifically, the more money a couple spends on their wedding, the less years they will spend married. Does this mean that spending a lot of money on your wedding causes you to get a divorce? Whoops. No, because even though, correlation doesn't always mean causation. There may be other lurking variables causing the correlation. Just because it's a high correlation showing that people who spend more money on weddings are married a short amount of time, just because there's that correlation that shows that, it doesn't mean that, oh, if you spend a lot on your wedding, you're not going to stay married long. That's not a direct causation there. 14, the probability of event is the proportion of the times the event occurs in many repetitions. Now, number 15, a principal has found that the correlation of GPA and attendance can be given by the equation below. So predicted GPA equals 1.5 plus 0.125 times the attendance percentage. So look what I'm writing up here. That's kind of like our equation. I mean, it is. And so we see our slope would be the 0.125, our y-intercept would be 1.5. And so, the slope and the x value is the attendance percentage. So they want to know as a student's percentage, their attendance percentage increases, what happens to the GPA? And how do we know this? So because our slope is positive, GPA would increase because the slope is positive.